and welcome. We've been doing a lot of lectures on eigenvalues, eigenvectors, and various different properties. We're going to now put it to use in a very important electronic systems problem, okay, digital filtering, FAR filtering, okay. So the idea is called circular convolution and circulant matrix. There's going to be a lot of notation here, but hang on, try it with a few examples if you want to get a clear picture. But this is a very crucial idea when you start looking at digital filter design, digital signal processing. This idea is very important, okay. So what I'm considering here is what's called an FIR filter. It's got an impulse response H0, H1, H2, H3. Think of these as some complex numbers if you want, okay, or real numbers or complex, whatever, okay. Now this filter has a input which is a sequence of numbers. Once again, this could be real numbers or this could be complex numbers. But wonder, how do you get complex numbers as signals? Complex numbers are nothing but two real numbers, no? Real part, imaginary part. Quite often, that's how we think of a complex number, right? It's convenient to think of two real numbers as one complex number. These are called I signal, Q signal in some communication domain. It's convenient that way, okay? So here is a sequence of inputs. So it's 0 before and 0 later. There are only like 5 inputs, x0, x1, x2, x3, x4. This is just for simplicity I'm doing. You can do for longer also. So when you have an impulse response like this, and then what is this output? So there is a connection between this impulse response and input and output, and that is the definition of what's called convolution. Okay, this convolution is a very important idea which characterizes all these linear systems and linear filters and all that. Okay, so here is the relationship. Yn is H0, the first filter coefficient, times Xn. So Xn is the input at time n, right? So n is now my time index. The output at time n is given by Xn times some coefficient plus the system has a memory, the filter has a memory. The previous input will multiply by my first tap, as it's called. Okay, this is the 0th tap, H0, my first tap H1. H1 will multiply my input with a lag of 1. So the inputs come in, the inputs don't go away immediately, they stay in your system for some time. Okay, the input at the corresponding time gets multiplied by the 0th tap H0. The previous input gets multiplied by first tap H1. The previous input gets multiplied by H2. The 3 times previous guy gets multiplied by H3. And all these guys are added, linearly combined to give you my Yn. Okay, so likewise you will do. So now we'll see what happens. Y0 is H0 times X0. Why? Because previous to X0 they are all 0. So all these previous guys are all 0. So you'll just get this. Now Y1 is H0 times X1 plus H1 times X0. That was the previous input. Y2 is H0 times X2 plus H1 times X1 plus H2. You see the idea, right? Y3 will become these guys. After that, Y4 will be all easy to write down. Is that okay? So I'm writing X6, X5, X7 just for fun, you know, so give you a complete nice picture. In our specific example, X5, X6, X7 are 0. Okay, so these things won't come. So you will stop with only this. Okay, but anyway, I'm just writing it out here. Remember that it is 0. Okay. Now this is actually a linear transformation. Do you see that? The X0 to X7 are getting linearly transformed by some form of these impulse response coefficients to get Y0 to Y7. Okay, so that's why linear transforms and linear operators are extremely important. In fact, if you write down the matrix carefully, okay, X0 to X1 is X7 is input, Y0 to Y7 is input, what comes inside ends up being what's called a circulant matrix. What is circulant? You take the first row here, it will be H0, 0, 0, 0, H3, H2, H1. Okay, so remember X5, X6, X7 are all 0. Okay, so these things don't matter. If you multiply, you will only get H0, X0, right? So it doesn't matter, don't worry too much about it. But what is the second row? Why do I call it circulant matrix? The second row, if you look sharply, is actually a circular right shift of the first row. Do you see that? If you right shift the first row by one position, this H1 will come off to the first one. It's a circular right shift. The last guy, when it spills out, actually comes back to the beginning. And the H2 goes here, H3 goes here, 0 goes here, this 0 goes here, this 0 goes here, this 0 goes here, H0 goes here. Likewise, the third row is a circular right shift by one of the second row, and so on till the last one, which, you know, the full shift has happened, this H0 has come all the way to the end, and that's when you stop it. Okay. Another way of saying it is column wise. Look at the first column, it's easier, right? H0, H1, H2, H3. Second column is one shift down. Third column is 2 shifts down, 3 shifts down, so on, so on, so on, so on, circular shifts. Okay. So these matrices are called circulant matrices. Now, we've seen so far in our theory that diagonalizable matrices are nice. Okay. What about the circulant matrix? Is it actually diagonalizable is a question, right? If it were diagonalizable, maybe we can understand the circular matrix much better. Okay. We can understand our filter better. We can design filters better. Okay. So, how do we think of circulant matrices with respect to eigenvalues and eigenvectors? That's what I'm going to show you next. Just for convenience, so in the previous example, I had all these 0, 0, 0, 0 because I was only going up to H3. But I'm going to simply put them, I'm going to fill these up, not stop at H3 here, H0, H1, H2, H3. I'm going to do H4, H5, H6, H7, just for comfort, right? And then I'll do the cyclic shift. The circular shift I'll keep doing carefully, okay? That's what I've done here. I've not stopped at H3. I've gone to H4, H5, H6, H7, and then I've done circular shift, circular shift, circular shift, circular shift, so on to get all the other columns, okay? Just to consider the more general case. So it's an 8 by 8 matrix in this case, okay? So now, notice one interesting thing. So it looks a bit complicated. So one can intelligently, cleverly, because I already know the answer in some sense, can come up with some eigenvectors, eigenvalues. Here is the first one. V0 is the all ones vector, is an eigenvector of M, this matrix. Why? Because if I multiply by 1 on the right, I will be adding up all the values here, right? Now you see all the values, these guys are cyclic shifts. So all of the sums will end up being H0 plus so on till H7. So we multiply by all ones, it is H0 plus H7 times the all ones. So it becomes an eigenvector. You see that? You can sort of intelligently guess that this all ones will be an eigenvector. You can be a little more intelligent, use some really smart ideas of what's going on and guess more eigenvectors. Let's say alpha is an 8th root of unity. Okay, you remember 8th root of unity? I'll give you a value for it soon enough. But what does it mean to say 8th root of unity? Alpha power 8 is 1 and then none of these other guys maybe are 1, but alpha power 8 is 1 for sure. Okay, alpha is a complex number. Okay, and then if you take a v which is 1 alpha, alpha squared, so on till alpha power 7, sequence is a length 8 vector, no? If you multiply it on the right, I will leave it as an exercise. It's an important exercise. I'll urge all of you to do it. If you multiply it on the right, you will get actually that this is an eigenvector with eigenvalue H0 plus H1 alpha inverse plus so on till H7 alpha power minus 7. You can quite easily prove it. It's just the cyclic shift and this powers. These are also cyclic shift, no? If you multiply by alpha, right, you actually get a cyclic shift. Okay, so it's a powerful property of this alpha power 8 is 1, right? Alpha times V is actually a cyclic shift of alpha. You see that? Cyclic left shift. Okay, so that's the powerful result here. Because of that, this eigenvector property comes. I'll urge you to check it. It's a very easy thing to check. You just have to write it down and show that it will be exactly this constant times the same vector again when you multiply the m of t by m by v on the right. Okay. So this gives me a nice little idea here. So I know alpha, right? What is the primitive 8th root of unity? It is e power I 2 pi by 8. You have seen this in math 1. Go back all the way and check your complex lectures. The primitive 8th root of unity, basic. So you remember the unit circle, right? It goes from 0 to 2 pi, and then the e power I theta is on the circle, cos theta sin theta, and then if you want 8th root of unity, you have to do e power I 2 pi, which is 1. You divide e power I 2 pi by 8, right? So e power I 2 pi by 8 is the primitive 8th root of unity. This is usually called W8 in the DSP parlance. You can call it anything else you like, but W8 is sort of standard. So once you do this, I can now start writing down all the eigenvectors. So first eigenvector is putting alpha equals W8 power 0, which is just 1. If you put alpha equals 1, you get back your first V0, right? V0 is 1, 1, 1, 1, 1. The eigenvalue is summation j equals 0 to 7 Hj. Okay. And then you can write this down. I've just ridiculously written something. We'll come back to this later. Now for k equals 1 to 7, I can also put alpha equals W8 power k, right? So if you think of the unit circle, 2 pi by 8 is something, 2 pi by 8 into 2, 2 pi by 8 into 3, like that. I can multiply. All those guys are all 8th roots of unity, right? So I can put different values of k here, This will give me Vk, which is 1 alpha W8 power k, alpha square W8 power 2k, W8 power 3k, so on till W8 power 7k. Okay, what about the eigenvalue here? I have to do alpha inverse, right? So, summation j equals 0 to 7 Hj alpha inverse power j, right? So, W8 power minus k over j. So, if you add this, you get the eigenvalue. So, you start seeing complex eigenvalues. We will see a specific example later on with the smaller size. This is 8 by 8, it is quite big, right? So, you can do 4 by 4, you will get a smaller size. But this is the central property. So, I wanted to just think about it. So, the circulant matrix that we picked up with is actually, it's got a whole bunch of eigenvectors. It's got 8 different, this is 8 by 8 matrix, it's got 8 different eigenvectors, okay, with looks like 8 different eigenvalues, okay. So, if these 8 vectors, eigenvectors end up being linearly independent, then you have diagonalizability. It turns out it's true, okay. So, we will see all these properties later on. This V0 to V8 are V7 are very special. They end up being linearly independent and all that, and you have these eigenvalues. These eigenvalues have a special name. These are called the discrete Fourier transform of H1 to H0 to H7, all of that. You will learn more in your signal processing literature, but linear algebra is at the heart of linear filtering. Okay, good. So, let us see if we can use all our clever facts to quickly find out eigenvalues and eigenvectors for these two examples. What are these two examples? Let me start with the first one. Well, I will start with the second one. Second one is circulant, right? It is circulant. So, it is very easy to do. So, let us do the second one. The matrix M is just 1, 2, 3, 4, and then I have done my circular shift, right, 1, 2, 3, 4, okay. So, now this is 4 by 4. So, my W4 will be e power I2 pi by 4. This is e power I2 pi by 2. What is e power I2 pi by 2? It is I, okay, cos theta plus I sin theta, okay. So, it is I, and what is my V0? V0 is 1, 1, 1, 1. We just write it as 1, 1, 1, 1. Eigenvalue lambda 0 is just sum of all these things. It is 4 plus 3 plus 2 plus 1. What is that? That is 10, right? That is good. Now, V1, okay, is going to be W4 power I, right? So, it is 1, and then I, W4 power 1, W4 power 1, W4. So, this is alpha equals 1, this is alpha equals W4, which is I, no? It's I. So, Vi is, remember, alpha, once you put an alpha, it's alpha, alpha squared, so on. I squared is minus 1, and then you multiply by I again, you get minus I. And what is lambda 1? Lambda 1 is 1, 1, 2, 3, 4 is H, right? So, 1 into, so this alpha inverse, right? So, 1 plus 2 into alpha inverse. Remember, alpha inverse is what you have to multiply, so it is minus I, okay, plus 3 times alpha power minus 2, so it is minus 1, then 4 times power 3, which is minus I, okay, so it is I, right, alpha power minus 3, so it is I power minus 3. Remember, if you want, you can write it down. I squared is minus 1, I power minus 2 is also minus 1, I power 3 is I power minus 3 is, I power I is minus I power minus 3 is I, okay. So, 1 by minus I, it's I, okay. Then so on, right. So, you can just do that math a little bit. So, then you have alpha W4 square, which is I squared, which is minus 1, right. So, you will have V2 being 1 comma minus 1, then minus 1 square, which is 1, minus 1 cube, which is minus 1, okay. So, this is easy to do. So, when you have, see, another way to do the eigenvector is just to find the first coefficient. So, this should be 4i minus 3 minus 2i 1, right. So, this would be, if you want to write it down, it is minus 4, right, minus 4 plus 2i. Another way to quickly do this is you simply do m times 1i minus 1 minus I and pick the first element, okay. The first, you will get a lot of things here. This one will be lambda 1, okay. You can quickly check that. That has to be true, no, just the way the property of the matrix comes about, that has to be true. So, we can use that fact here. So, 1 minus 1, 1 minus 1. you multiply by V2 and just pick up the first k, because it always starts with a 1, no? So that gives you that. So you can go back and put in the formula also, but you will get the same answer, okay? So minus 3 plus 3 goes off, so you will get minus 2, okay? And the last alpha W4 power 3, which is minus I. So V3 will become 1 alpha squared, which is minus 1, and alpha power 3, which is I. Okay, and lambda power 3 is just the first k multiplying this. So 1 minus 4i minus 3 plus 2i, which should hopefully be, minus 2 minus 2i. Okay, so that's what I'm getting. So you can check the math here. Maybe I made some mistakes. Hopefully I didn't make a mistake. So hopefully it should be okay. Okay, so that's the first one. Just use the circulant property, use the various formulae you have, you get to the answer. Look at the next one, 1 0 1 0 1 1 minus 1 2 1. Let's look at this one. 1 0 1 0 1 1 minus 1 2 1. Okay, on the face of it, it looks like you have to write formulae and all that, but let's try something else. The first thing you should try is row sum, right? If you row sum, you see that the row sums are all 2 2 2 here. So once the row sums are the same, you will get eigenvector is 1 1 1 with eigenvalue 2. Right, so the row sum is the eigenvector. So 1 1 1, we found one eigenvector, nice enough. The next thing to try is to see if there is any null space vector. Okay, so because null space vector is there, then you know there's an eigenvalue 0 also, right? So let's check if there's a null space vector. So you have to see if you have to do elimination to try out and see if the rank is going to go less than 1. So you've got first pivot here, 0 is okay, so you have to add this to 2. There you go, we've already got it. And the next step in the elimination is 1 0 1 0 1 1 0 0 0. So there is a null space vector. So how do I find null space vector? 1 0 1 0 1 1 minus 1 2 1 times x1 x2 x3 equals 0 0 0. Okay, so I can do the same thing. I can sort of eliminate with this. So this would be the same as 1 0 1 1 0 1 0 1 1, right, equals 0 0 0. So this would be a free variable. You put a free variable here, then okay, if you want, let me write it down, 0 1 1 x1 x2 x3 equals 0 0 0. Okay, sorry, last one is gone, it's just 0 0. Okay, so this is a free variable. So I'll put x3 equals 1. There's only one vector in the null space. You put x3 equals 1, you get x1 equals minus 1, x2 equals minus 1. So that should also be an eigenvalue. So minus 1 1 with eigenvalue 0. Okay. So once you have two eigenvalues, so I know my sum of the three eigenvalues is what? Lambda 1 plus lambda 2 plus lambda 3 is actually 3, right? Trace is 3. Okay. So what should be the third eigenvalue? Is 1. Okay. Once you have the third eigenvalue as 1, it's just a question of finding out the null space corresponding to that. 0 0 0 0 0 1 minus 1 2 1, and that will give you an eigenvector which is 2 1 0. This is eigenvector with eigenvalue. So if you do 2 1 0 2 1 0, I think it's an eigenvalue 1. We already saw that has to be the eigenvalue 1. 2 1 0, you can check. 2 1 0 is 2, 2 1 0 is 1, 2 1 0 is 0. Okay, so eigenvalue is 1. So these are the three eigenvectors: 1 1 1 minus 1 minus 1 minus 1 minus 1 1 with eigenvalue 0, 2 1 0 with eigenvalue 1. So you can quickly find out. So notice how I used the various facts I knew about eigenvalues and eigenvectors and quickly found out the eigenvalue without solving any polynomial equation. In this case, actually, even the polynomial will be very, very simple. Nevertheless, you can do it in a smart way bigger cases. Okay, so that concludes our discussion of diagonalizability and eigenvectors. Thank you very much.